Here we go. I'll start with a brief history of logics and ontology engineering. Then we'll talk about logics that are used in ontology generally. And then I'll talk about this kind of subtle feature of these logics or subtle proof technique used in these logics or about these logics, which is useful for you to know. Let's start here. So researchers across the sciences typically use a formal language when they're being really careful called first order logic. And it has the following vocabulary. Vocabulary just mean like, how do you construct sentences in the language? Well, you use this stuff. You use like logical operators, like not, or this tilde for not, an arrow for if then, like if this then that, and ampersand for and, this and that, lowercase v for or, this or that, etc. And then these last two, for all and for some, these quantifiers. For all, it has a little underscore there. This just means you can fill things into it. That upside down A, for all, just means anything within the scope of whatever is filled into that placeholder. And then the backwards E there, existential, we call it, that is for some. So for all, for some. This is basically the ingredients for first order logic. And you can express quite a bit with this in combination with what we call predicates in the language, like P and R with one space. That is to say, they take one argument, or P space space, R space space. These are relations. They relate one thing to another. You can also relate multiples, more than two things, like between this is an example. John is between Sally and Sam. Like that's three things that go into that. We represent all of this in first order logic. As you can see, we also have variables. And these variables can be used to fill in scope of the quantifier. If I put like for all X, I mean everything. If I say for some X, I mean something in the domain, right? The variables, they work just like they do in math, right? Fill it in, anything from the domain should satisfy the expression. They also can go in to these relations or these predicates. John is between somebody. John is between everybody. And also, lastly here, punctuation. These are just like to disambiguate expressions. So once you start combining complex expressions based on this vocabulary, sometimes you need to put parentheses here to make sure that one thing's being evaluated over another. This is basically the ingredients for first order logic. If you're looking at like a really careful scientific text, you'll see these symbols. They come up everywhere. Let me explain a little more. All bald men are happy. I only have an N of 1, but so far it's true. If you want to go from this English expression, natural language expression, into this more precise formal language, you can do it in steps, like paraphrase steps, I call them. You get a little more technical as you go through. Here, all bald men are happy. What does this mean? Everything that's bald in a man is happy. Okay. A little more precisely, for every X, there's a variable. For every X, if X is bald in a man, then X is happy. Seems like it's tracking very closely the expression all bald men are happy. Something satisfies being bald in a man is happy. And you can see this more formally in that vocabulary I was just describing. So for all X, if X is bald and X is a man, note that the X here binds the scope, we say, of the variables that come after it. So the X's are all, that X is connected to this quantifier. So is that one. And in this case, when we fill in X for the happy people, also that quantifier is binding that last variable. Now, what does this mean though? Because right now I've just been talking about the vocabulary and how you might like translate natural language into a vocabulary. But those are just symbols. Symbols, we're moving around. What do they mean? They're supposed to mean something. Let's look at the example and we'll say the interpretation or the meaning of the sentence. For every X, if X is bald in a man, then X is happy. What do I mean by for every? All the things. That's what I mean. We say quantifiers open. I mean it all. I put no restrictions on them. What about if, then? What does that mean in this context? There's where the restriction comes in. For every is everything. And now I'm saying, I just want to focus on bald men out of everything. So if something's a bald man, let's talk about that. Here are the bald things. Here are the man things. I'm just interested in the bald man things right there in the intersection. That's what that and is doing, right? Cutting the intersection between them. Now, what about the then? Well, I want to say, out of all the happy things, and this was just an accident, I didn't actually mean to say that all men are happy, but that's what this represents. So forgive me for that. But as you can see, because all the man things are in the happy things, so technically. Okay, but what I really was trying to do is all the bald man things fall within all the happy things. That's what I'm trying to get at. And that's what this expression means. For everything that's a bald man thing, it is also a happy thing. Does that make sense? In addition, this vocabulary. We also add names for things. So far I've just added like variables. I mean, in the examples I was talking about John, but strictly speaking, I'm not representing any John in everything above the names, right? There's no John in there. If we want to represent John, we got to add some names for John. I'm not a variable. We could be like Alex, Bob, Chris, Deborah, just lowercase letters is what we use. There I am. Someone is bald and happy. True. I am also true. In fact, me being bald and happy is a little lowercase j representing me entails that someone is bald and happy, but not the other way around. If John is bald and happy, it follows that someone is bald and happy. If someone's bald and happy, it doesn't follow that John is bald and happy. Yeah. There's a subtlety in the quantifiers. But we can represent both and many more besides. We can represent John having an arm that's part of him right here. Part of A. A is my arm. J is me. John has a sister, Kelly. We're related. You should say sister, but sometimes I don't feel like I want to be her brother. But anyway, John is between Sam and Deborah. JSD, Sam and Deborah. Right? 3-place relations. So far, so good. Formal language used all over the place. It's very expressive, which is one of the reasons why it's used so often. Here's a textbook about like the foundations of science. It's all first order logic, right? Now, you may have heard that the language of mathematics is the queen of the sciences, though. You may have heard that. People sometimes say that. And I'm talking about logic, right? Logic isn't math. Math's about numbers. Math is based in first order logic. Just want to spoiler alert, just let you know. It is. It is. Absolutely is. The interpretation of all. Somebody like nodded as if this is not true. This is absolutely true. Yeah. The interpretation of everything is based in first order logic. Now, it is, again, the foundation of all the sciences, the language they use. Note, I said it's, oh, Jay's got a question. Hello, Jay. Jay, yeah.
I got to unmute myself. So question, so just because first order logic is correct in a statement like all bald men is happy, it doesn't mean that necessarily it's true. And you need a larger model with first order logic about everything to be able to really tell that. But if you just have that one statement in a silo, it can look true, but in reality, when you say you put it in the BFO or something, it's not true. Right?
Absolutely right. Absolutely. We got to be careful. We got to be careful when we're formalizing these things and like asserting there's truth associated with them, because I mean, that expression, bald things, if I'm just narrowing down to this room, all bald guys, me and Rob, like we're both happy, but that's not everything. Now, of course, I could restrict the claim, say all bald people in this room. Maybe I'm getting closer at it, but this is an important point. This is an important point about being careful and clear about what you're saying too, because I suspect it is the case that there are bald people, bald men who are not happy. I've met a few. Very good. Now, I said first order logic is expressive. It's one of the reasons it's so valuable. It is too expressive. It is so expressive that it is undecidable. In fact, if you take that interpretation of the quantifiers I just gave, where they're ranging over this and ranging over that with the variables, and you allow for more than 2-place relationships, so more than like John is next to Sam, if you allow for things like betweenness or having a part at a time, that's all you need for a language to become undecidable. What that means is we can't determine in this language that for every expression, whether the expression is false or we just haven't found a counterexample to it. There is no step-by-step procedure we could conduct to evaluate truth or falsity that always terminates for every first order logic expression. That's undecidable. Now, we can, of course, construct algorithm step-by-step procedures that can evaluate and terminate. We can trust terminate for a large group of first order logic expressions, but not all of them. And that is what it means ultimately for first order logic, the language to be undecidable. That thing I've said here, no step-by-step, we call it efficient procedure for evaluating the truth or falsity. Now, why is this important? Well, the observation of the undecidability of first order logic led to computer scientists back in the day to reflect on how the expressivity of first order logic might be restricted so that the result was a decidable language. And this was important because computer scientists were trying to use a formal language for which they could trust there would always be a termination of truth or falsity for the expressions represented in it. They didn't want to have to guess whether something was potentially false or there was just a loop, because loops happen anyway. And that's kind of a poor epistemic situation to be in. You don't want your software to like be looping and you not know if it's just false or just looping. Now, the idea here was to find the most expressive version of first order logic that would not result in undecidability. And this created a research program started around the 80s, continues to this day with varying degrees of success. And it's spurred the creation of new logics based on first order logic called description logics. Yeah.
So is like an example of this one, like predicate has 3 arguments. Like Sally is in between John and Sam to the left of the tree.
Yep. Yeah. So there's actually yeah, if you have a ternary relation, and the usual interpretation of the quantifiers in the first order, as you do in first order logic, then you can generate an undecidability, or you can prove that the language has the same level of decidability as what is it called? The not a turn, it's the other thing, the halting problem, which is how folks like that's how proofs work in complexity theory. If you can reduce a language to the halting problem, and that shows that the language is undecidable. It doesn't tell you what expression generates the issue, but it does. It is like a meta proof about it. It's one other thing to point out here. When I say usual interpretation of the quantifiers in first order logic, I mean the domain is infinite, potentially infinite. That's an important piece. As we'll see in these description logics, the domains are assumed to not be infinite. And they're assumed you're not allowed to have more than 2 place relations. And those 2 pieces combined allow you to create a decidable fragment, we say, or guarded fragment of first order logic, which we call description logics. And there are many flavors of description logics, many different strengths. You can change the details of the logic in different ways and get more or less strength, more or less expressivity. Now, description logic is, as I said, a family of logics designed to be expressive, decidable languages based on first order logic, so that we want to be able to use languages based in this, put them into our computing environments, and trust that they will terminate truth or falsity and not just loop forever, unless, there's just a loop. So most relevant to us as ontology engineers is that description logics provide a theoretical foundation on which the web ontology language is based. And OWL is what we use for the most part, but we'll talk much more about that in the next lecture, where I'll tell you like the history of RDF, RDFS, and OWL. But this is like the language we use to represent logical relationships in ontologies. And it's a W3C standard. It's very widely used. This is our baby. Now, in the remainder of this lesson, we're going to explore description logics of various degrees of expressivity. And in doing so, we're going to gain a theoretical understanding of the backbone of OWL. And what we're going to do when we're, like, for instance, working on project 1 is going to be very OWL specific. Now, we're going to leverage both knowledge of OWL and knowledge of its logical foundations in a way that people don't usually do when they're talking about OWL or publishing on OWL, to like illuminate how OWL can be used and what you should be using it for. Okay. Again, most people don't. One, they either like understand how to use OWL in this or that case, or they understand the logic. Never the twain meet very often. We will meet in this class. Yes, Jay?
2 questions. well, maybe they're not even questions. So that's why we use in BFO all the time some, because the universals are so expansive that, some people have two legs, but not all people have two legs. Right? Is that correct?
So what I think you're pointing to is that when we place property restrictions or restrictions on classes, we're talking about like the class of all humans, and we want to say something about the like features that humans have, like they have hearts or something. Like maybe you want to say that in your database, all humans have hearts or something. The way the logic works in OWL is the restriction is by default, you'll say all of the things in this class have some instance of this other class. And that is a safe way to talk about the relationship between instances of all the instances in one class and their relationship to another. There are other ways to do it. You could say, for instance, and we'll talk about later in this class, actually, you could say things like they have only hearts, which would be false. But that only part, you can say that. It's very tricky to get that right. And so by default, and you'll see this in like Barry's Building Ontologies book, like a heuristic, we follow what we call the all sum rule. And that all sum rule is that first characterization I give. All the things in this class have something of this other, rather than what you might call the parallel being the all only rule, which is all of the things over here have only things of this class. Most often that second case is false. Most often the first case is true. So it's a heuristic that we use, but we'll see much more of that. We'll see some of it here, and then we'll see it in action later when we're dealing with OWL proper. Does that make sense?
Yeah, and then my second question is just, I've heard web ontology language be referred to as a predicate logic language. So is that why first order logic falls into that? Or is that just a really bad
way
to call that?
So I'm going to be the persnickety logician that I am inclined to be, that I usually don't get to be. Because we're talking about logic, I'm going to say that's a bad way of characterizing. It's not a predicate logic. A predicate logic has, you have adicity greater than 2. You have the quantifiers. A predicate logic has a specific name. Like it's a specific type of logics, like common logics or predicate logics. OWL is not a common logic. OWL doesn't have that kind of expressivity. It also has features that like predicate logics don't have. As we'll see here, we're going to talk about some of them. They have role constraints that operate like on classes of things. You don't get any of that in first order logic or any of that in predicate logics. There's, in a sense, like additional expressivity that could be reproduced in first order logic, but it's actually part of the vocabulary of the description logics. So the persnickety logician in me would be like, no, don't say that. They're like classes of logics. But great point.
Can I ask a quick question?
Yes.
So like on the first part that he said, is that how you determine like what properties are always going to be inherited by the child class?
Not quite.
No.
But it does help you, and we'll see some of this. It'll help you see what sorts of connections you might want to make in a safe way between classes and other parts of the hierarchy. Yeah. But we'll see more of that in some detail. Yeah.
So description logic does not assume an infinite number of objects in the domain.
That's right.
A lot of models, like especially in economics, do assume an infinite number of objects, and number theory too.
Yep.
Does that create a problem for representing those models within ontologies?
I don't think so, for the following reason. So in the economic case, I don't want to represent all of the minutia that they're representing. And the same in the math case. If you come to somebody and they're like, build me an ontology of math, and you start making classes or instances for numbers, you've done something wrong.
If you make an ontology of economic theories, though, some of those theories assume an infinite number of objects. Can you represent that?
Absolutely, as information, because they're theories.
Okay.
Now, what they're about is a different thing.
Yeah.
Are they about anything?
I mean,
Maybe.
Idealizations.
Yeah, exactly.
So
are they about an infinite number of things in the world? Or are they a theory that is like using an abstraction to do that? Which is fine. We can represent generically dependent continuum information like that. That's fine. Okay. Like we can represent first order logic as information, as a language in BFO. We don't, but again, this is what I'm pointing to. I'm saying if somebody comes to you and says, represent like mathematics, represent number theory, and you start building numbers, you've done something wrong. Because that's not what we do. We're not trying to duplicate the theory. We're trying to represent the theory.
Would you treat the theory as a class and an individual?
So sometimes when this comes up actually when I'm dealing with like psychology theories, which are some of the projects I'm working on right now. I think of specific theories as instances, like what's his name? Maslow's hierarchy of needs. That is a specific theory. It's Maslow's, right? It's not a class of things. There's no like instance of Maslow's hierarchy of needs. It's a theory that's about stuff. Hopefully, if he was right, it's about something. And people use that instance of a theory to like as proxies for various measurements they conduct in a way to like either confirm or disconfirm. And it has parts. It has like constructs, they call them, that hopefully will translate into other theories so that you can like do inter-theory reliability analysis or something like that. But yeah, like
Yeah. So John, if I was using E equals MC squared,
say that
right?
again?
If I was using E equals MC squared, right?
Mhm.
Wouldn't I want to have that as a class so I could have universal relationships to it, but then I would all want to use it as an individual so that I could use it like in other equations?
So what instances would it have?
I guess it would just duplicate itself. Like, you know how like some ontologies will have the IRI is a class and then the same IRI is an instance,
Yeah,
right?
you can
That
do
way
this.
you
It's
could
called punning.
have it be its own type, but then you could have universal relationships to it, saying like this has a relationship with time and speed and everything else. And then if you need it as an instance, you use it as an instance because you're going to put it in other equations. But could you put a class in another equation, or would you want to use that?
Not if you're representing it in OWL. So like all the relationships, like you're not going to be able to like relate a classes to classes in OWL because the object properties only relate instances to instances. And so like, but there's what you're pointing to, I believe, is a strategy that people use when they want to actually do that sort of like relation building for class-like things. It's called punning, where you create like an instance for the class. And so you have like dogs or dog as a class. And then you say, I want to like connect dog as a class to various other things. And so what I do is I introduce a name that's supposed to like be a pun on the class dog. And I'm going to use this to represent, the class dog. Now you can do that. There is no logic around it in OWL. There is no connection between the class and the instance. They just have the same name.
Yeah. I mean, you only have that you can call it a type of the class.
That's right. That's
You
right.
have the connection, and it just inherits everything from the class. But
Mhm.
so would you want to create two separate IRIs then for that and have the class be its own entity and then have the instance of it be its own entity, or would you not want to do
You
that?
would have to create two different IRIs because if you didn't, you would be attributing both the class and the individual properties in OWL to it, and that would take you outside the scope of OWL 2 and into OWL full. But if you're already going to go into OWL full, in OWL full, you can relate instances to classes and classes to classes with object properties. So you might as well just do that. But that is actually what we're going to talk about next time. So great questions. But is it okay if I continue on through here? Do you mind?
Oh, no, I'm
Okay,
done.
cool. Okay, just want to make sure, unless you had another. So, okay, so I just want to make sure I don't lose everybody else because I think you and I were about to start having a punny conversation. Wink. Okay, but now with that background, let me talk about description logics. These things I've been gesturing at. So basically, they're logics that start with first order logic and add the following constraints. So relations of no greater arity than 2 are allowed. This is what I've been pointing to as a binary fragment of first order logic. In addition, in these logics, the same object can have multiple names. This is not true in first order logic. So I am named John. I am also named Papa, what my daughter calls me, or Chris, you're in the South. I have multiple names. I'm one object. This is the unique name assumption that is being rejected in this language. So first order logics, the names pick out one thing. In addition, just because you don't say something doesn't mean it's false. In first order logics, you don't say something and on that interpretation, it's false. But that's the closed world assumption. In description logics, we adopt the open world assumption. Just because you didn't say something doesn't mean it's false. As you can see how this would be valuable if you're dealing with information under uncertainty, Just because I didn't say something about so-and-so buying lemons at the store the other day doesn't mean they weren't. If you're putting this in the context of the previous lecture, you've got something of, we allow for rebutting defeaters here and undercutting defeaters. So.
If you make the open world assumption, do you end up with like a, I'm blanking on the word for it, but, like an intuitionist logic, like a three-valued?
No,
Like-
because we don't put evaluation on it.
Okay.
So just because you didn't
So-
say it doesn't mean anything.
So then what do you, for those sentences that don't have anything about them, like what truth value do they take in this?
Nothing. We don't say anything about it.
Okay,
Just, I mean, we wouldn't know to.
that feels like.
This is very similar. I mean, it does say share similarities with intuitionist logics, but we don't have like the hard sort of negation by proof stuff that goes into it. It's just like tableau reasoning, which is all indirect, which we'll talk about. So there are a lot of differences between this, like description logic and intuitionist logics. But I'll tell you this, just because you piqued my interest. Intuitionist logics can be translated into S4 modal logics. There's a mapping between them.
Yeah.
Description logics have a very natural translation into modal logics. Some of them are S4. Yeah, for the most part. Patrick Blackburn and Carnegie, students at Carnegie Mellon, several of their dissertations are coming out that are about this very fact. So the relationship between characterizing, like, you can characterize a lot of description logic as modal logics, which should make sense. Description logics are fragments of first order logic. Modal logics are fragments of first order logic with a saturated signature to allow for like modality. It's all within the big wedding cake that is first order logic. Okay, so syntax. Remember, I started with the vocabulary of first order logic. This is the one that should both frighten you and also you should pay attention to more. This is the ALC syntax. This is the base description logic, the simplest one, and it means something like attributive logic concept. I don't remember, nor do I care. It's ALC. You'll see there are going to be a lot of acronyms here. I don't ever bother to try to remember what they mean. So, but the important part here, definition. Let C be a set of concept names and R be a set of role names. You should read that as seeing like classes and relations. This syntax was created by computer scientists who had strong opinions about naming things and it's very confusing. Just see class and relation, C and R. The set of ALC concept descriptions, this is just the vocabulary that we're interested in, over C and R is inductively defined, and I'm not going to tell you what that means because it doesn't matter for us, but you can define the vocabulary basically in these terms. Every concept name, every class is an ALC concept description. This uppercase T and this lowercase t are included as concept descriptions. The first means true, the second means false. Logically, it's the top and the bottom of your domain. Don't worry, I'll talk more about that in a second. I've got some diagrams if you're more of a visual learner. I just want to talk through this. Now, C and D are ALC concept descriptions and R is a role name. Then you also have these as concept descriptions here. And these are just ways you can combine the classes and relations. As you can conjoin them, you can disjoin them, you can negate classes, you can put quantifiers next to roles over classes, and in both cases. Now, I can see some eyes glazing over, and that's okay. It's like I said, I have pictures. These are easier to grasp. This thing up here, those symbols, in logic, we call it the signature of the language. So if I say signature, this is what I'm talking about, just the vocabulary, right? The concept descriptions, all those I just talked through, I'm going to show you visually. So C, this corresponds to classes like teacher and reindeer, which are often assumed to be collections of similar enough instances in the world like John and Rudolph. Don't spoil this for me. I'm still waiting on him to come visit me one day. Roles corresponds to relations holding between instances such as loves or parent of or next to. See? John and Kelly, that's my sister. She's not a teacher, but for the sake of this example, she is. T, that really confusing thing I said a minute ago about truth. T corresponds to everything in the domain. And in practice, this is used to represent the most general class, the ultimate parent class of all other classes. It's in gray there. Thing. Teachers and reindeers fall under it. Everything does. In contrast, lower or like upside down T corresponds to nothing. In practice, this is used to represent the least general class, the empty class. Teachers and reindeers fall outside of it. There are no instances. And then, of course, you can combine these things. You can union classes together. It corresponds to the grouping of the C union D. I've even caught myself here in the description because I just said union. Corresponds to the grouping of all instances of classes, or class C with the instance of class D. This is sometimes imprecisely called the union of C and D. Similarly, there is the sometimes imprecisely called the intersection of C and D. It's just those things that are in common between, in this case, teachers and reindeer. Now, negation, this is an important one to point out. It's often overlooked. Very important, though. Always will be. It bifurcates the class. Negation works like this. When you put negation in front of a class like this, what it does is it bifurcates all of the things. There are going to be C things and there are going to be not C things. And you can see there's a line here between them. What's the class of smokers? People that smoke. What's the class of non-smokers? Plants. Tables. There's a joke there, but you get what I'm saying. If you put not smoke, okay. Now, here are the more subtle ones. These are worth belaboring a little. I want you to read it just like this. This backwards is existential R dot C is the worst notation you will ever see in the history of logic. Putting Quine aside, this is garbage notation. I hate it. But here's what you should see, or what you should read when you see this. There's an implicit universal quantifier right before the existential that says for all X, there is some Y, that E is ranging over a Y, such that if X is related to Y, then Y is a C. That's how you read that. I'll say it again. There's an implicit universal quantifier in front of the E that ranges over an X. And it goes, for all X, there is some Y such that X is R Y, so X is related to Y, that's what that R stands for, and Y is a C. This corresponds to all instances, there's that universal, all instances that are related to some C. But you can see an illustration here. These arrows will satisfy, right? Everything in here, we'll say there's just two things in teachers, right? That class is consisting of two things, it's just me and Kelly. All these things are related to some reindeer through the loves relation. Because again, if you were to spell this out, it would say every teacher loves some reindeer. Or really more generally loves something. And in this case, if it also had loves some teacher, if that was true, it's got another relationship here. That's fine. Again, if I didn't say it, doesn't mean it's false. No. It's false, right? So, but this contrasts with this case. Again, there's a universal quantifier out front, just like in this one, and also an explicit quantifier. This says for all X and all Y, if X is related to Y, then Y is a C. So in the previous version, I said, and Y is a C. In this one, I said, if, then it's a C. There's a restriction. Remember what I was talking about? A restricting domain. Anytime you have like this quantification and that sort, it's a good idea to start putting restrictions on, because you don't want to talk about everything. And in this case, what I'm saying is everything in the teacher domain corresponds only to reindeers.
For the capital T, that's like within the context of the class of things you're talking about. Okay. And then if you're saying C represents a class of smokers, the negation of C, but then the negation of C is just C, right?
Yes.
Okay.
That's right. All right. So, the previous example, remember I had an arrow between myself and my sister. It said I love my sister. That would not be true here. If I were to say every teacher loves only a reindeer. My sister's not a reindeer. But this image that I've shown here is true in that scenario. This one wouldn't be, because Kelly's not a reindeer. It would be true here. So again, the important part, you look at this syntax, this very tortured syntax. You should read something like, the first corresponds to all instances that are related to some C. The second corresponds to all instances that are related to only C. Okay.
John, in your open world assumption there, you're only counting that John and Kelly are teachers and there are no other teachers though, correct?
Yeah. Although in one of these, I said, just assume that only teachers, but
Yeah, okay.
yeah. So let me pause here. Are there questions? Because I'm about to expand on the language. I'm about to say more, like add another symbol that will allow us to say more. Because ALC, despite all of these cool things I just showed you can say, can't really say that much. It's kind of an inexpressive language. It's the base language on which all other description logics are based. And you'll see what I mean by that in a minute when I start adding machinery to it. Yeah.
The reason for the kind of implicit universal quantifier ahead of the existential quantifier there is that because we've said that falsity is in the dome is like an entity?
I wish there was something interesting like that. I'll tell you what it is. There's a convention in logics, whether it's computer science or in mathematics or whatnot. There's a convention that you never actually write down the first universal quantifier.
Okay.
It's just a practice that we've been doing for since the 20s, after Post did his characterization of first order logic that everybody started using because he's like, Frege, I did it wrong. I'm going to write a new notation. So everybody started using that. We just started stopping the use. And I actually put mine in. I think it's stupid not to. So, but who am I to object to all of the history of logic? ALC, base language for description logic. Can't say everything you want to say. You can say a lot, combining things, quantification, etc. But look, you might want to say, whenever you lay down a role, like a relationship like loves, you want to be able to infer information about its inverse, loved by. If John loves Mira, my daughter, if John loves Mira, it should follow that Mira is loved by John. Not that Mira loves me, she does, and I am loved by Mira. So loves is not symmetric, but inverse seems right. Does that make sense? So you might want that to follow, or to be able to have that follow in your language. And so far, given the resources I've described in ALC, there is no way to say that. Now I'm going to say there's no way to say that, but at the end of the lecture, I'm going to prove to you there's no way to say that. We'll prove it negative. It's going to be fun. But before we get there, this kind of observation motivated the introduction of another symbol to the language representing inverses, and the result being this ALCI extension of ALC. This is a stronger language. It can say more than ALC. And specifically, it can say something, it can relate inverses to one another. What does this look like? All right. John loves Snickers bars. Kelly, because she's stupid, loves Butterfingers. It's the same. Butterfingers are poor man's choice. Snickers, it's got everything you need. Okay, so loves, the inverse of loves, we could represent here with this minus symbol next to loves. Very hard to see, but it's right there. It just means inverse of. Just means loved by. So John loves inverse Snickers. If you were representing this in the description logic, that's how you'd write it too. Now, of course, loved by the arrow is going to go in the other direction, right? That's how we would interpret it. But because again, this syntax is stupid, they just put the little minus symbol and they keep the relationship the same, like the arrow directing the same way. That's not confusing, but this is how you interpret it, loved by. Okay. In addition, there are other things you might want to add to this language to bolster, make it more interesting. So again, building from ALC, I'm not using ALCI, that's independent. You can combine all of these things together, but right now we're just thinking about ALC and extending it to represent restrictions to no more and no fewer instances within the scope of the quantifiers. You can do that by adding cardinality constraints to the language. So if you for instance, added this less than or greater than, you can express constraints like the following. John is a person, he loves no more than 2 people, or no fewer than 2 people. And this is how you can enforce that constraint. Now you couldn't say this before. You had no counting, no cardinalities. You can also do this in a different extension, the Q extension, that allows you to restrict qualified cardinalities. What this means is cardinalities on specific classes of things. So not just no more than in things, but no more than in C's, no more than in candies, or no fewer than in candies. So you see, it's just an extension putting the class stuff in there. So the first one is just whatever. This is like classes specific. Yeah.
So this gets you the ability to quantify without identity then.
Yeah. Identity is built into it. We'll see. We'll see.
Okay.
Yeah.
So,
But
yeah,
that's right.
Because you just say there's no more and no less.
That's right. Yeah.
Okay.
You've got the existential and the identity built in. How do you do this in first order logic? You say it's all this and no more than that. Mhm.
Yeah.
So yeah. But instead of saying that explicitly,
You did this stupid
they
way.
pack it into so less than and greater than equality symbol. I mean, you see the equals to, right?
Yeah.
It's right there. Okay, in addition, there's another extension that's of interest. Nominals. I'm forgetting why they called it O, why the symbol is O, but ALCO, the O is for nominals. I think because N was used already, but in here, the signature, you might want to be able to represent in the language, just like we did in first order logic by adding names. You might want to be adding names to ALC. There's nothing I said up to this point that would allow you to talk about John Kelly specifically. Now you can. Not only that, but you can connect them to other things. You can connect names to other things. Now, this is a little tricky, so follow along. Now you might, like nominals allow for defining classes by the enumeration of instances. You say this class is just all of these things. For example, the Beatles consist of John, Paul, Ringo, and George. You might just want to say that's the Beatles, that's it. In ALC, the connective, that union, imprecisely, but union can be used to combine classes, not instances. Paul, Ringo, George, John, those are instances of things. They're not classes. So I can represent this, great bands, the Beatles, the Eagles, Metallica. But I can't describe the Beatles this way. I can't union John and Paul because the union doesn't work between instances like that. And what I do is instead, in this language, what we do is we take the set, the singleton set. That's what these brackets are for. So this is not just a name. It's an instance. It's this bracketing is mapped to, or the thing mapped to by the name. It is a class. It is a singleton class, so that I can use it with unions that only hold between classes. So now I can define the Beatles as the singleton of John, the singleton of Paul, Ringo, and George. Does that make sense?
The word class here is being used differently from how it is in BFO and it's not called, right? Like looking.
Sort of, yeah, because BFO is separate from the OWL implementation of it, and that's true. And in BFO, we talk about classes and we also talk about like categories
Yeah.
and universals.
Yeah.
And so BFO, we're using it something like closer to the mathematical sense of classes that's separated from like sets of things. And then the categories are like the primary, the principal classes. And then universals are kind of like throughout, right? And here we're using classes in just the set theoretic sense.
So you're turning John into a singleton class? I'm confused.
That's right. That's right. No, that's exactly what's happening.
And what is a singleton again?
It's just a set with one member.
So I wonder why.
So John, that set John, that with the brackets, that's just a singleton. It's a set that just has John as a member. And that is how that's how in the description logics, you're able to like enumerate using union, like elements, like instances. Yeah, what's that?
But it seems to me that we could do it in ALC without LCO, because
Mhm.
you could have like a stupid class like John class, we call
Mhm.
it, Ringo class, and Paul class, and it will have only one instance that is John in case, and then Paul. It's a stupid way of doing, but like it's very similar. So it seems like
Open world assumption.
LLC, and
Open world assumption.
open world assumption. So we could add.
How are you gonna say? Are you gonna say there? How are you gonna say there's only one member of the class?
Mhm.
Because the logic is such that it could be extended, so that John class could have two people in it, and unless you say somehow that you can't, the models allow for it. And so,
Couldn't you just use, with cardinality then?
oh, I thought we were just talking about ALC.
Well, no, I mean, like, could
You
you?
could,
get the
you could,
nomin-
absolutely.
Nominal to drop out if.
Yeah, you can
use-
do this, and sometimes as you'll see when we get to the zebra puzzle in this class, I will show you.
So is this gonna be
Sorry, the
represented
zebra
as a
puzzle.
class?
Huh?
So in your ontology, is this gonna be, is John now represented as almost, this makes him a class? So are you gonna have a class? And then John's gonna be an instance of the class, but then this other thing you created is gonna be a new class, which is John, which is the instance?
So anytime, if you're like opening this up in Protege, and you can actually write what I've got here, the John and Paul and stuff, you can
Yeah.
put in like the syntax state, you can put John or Paul or Ringo or George is like an equivalence axiom.
Uh-huh.
Now, what's going on is that the logic is being interpreted just as I've described here. Those become sets of things that are union together, using an or as a reflection of the union.
Okay,
This is exactly what's happening, even though that's not how you would write it.
okay.
Now,
But
you
you don't
could,
have
if
to
you want
build
to check.
another IRI. Do you have to build another IRI, or you use the same IRI from the instance of John?
Yeah, you don't have to use a different IRI. And in fact, if you wrote the axiom with the brackets, it'll still work.
Okay, I'm thinking about this in the form of like an F22. So
Mhm.
like saying that like, okay, say we have instance data for like 1,000 F22s, but only these 10 are in this squadron, right? You would do the same thing here for that.
That's right.
But what you're saying is you only have to have that one IRI ever for John or for Paul or Ringo.
Yeah,
You're just using this logic language statement to build that.
that's right. This is just how it works under the hood, as it were. But like, yeah, you're right. Like the IRI is going to sit on top. And
Right.
like interpretation of the IRI, like, I mean, I'm like spelling out more precisely what the interpretation is. So you
Okay.
can, it's like, you can see the nuts and bolts.
And I can do this in Protege.
Yeah, you can do it.
I think until I do it in Protege, I'm not gonna fully, like, I'm kind of
That's
pressing.
fine, yeah, go for it.
Yeah.
But as you'll say, I was mentioning like the zebra puzzle when we get to that, and you've probably heard some people groan because it's like the hardest puzzle in the world. In the zebra puzzle, I do this sort of enumeration in my solution using just the cardinality constraints without using the brackets, but you could just as easily do the brackets. But yeah,
I mean, this seems. I don't know, this seems very Quiney to me, like.
you mean like
you know-
Pegasizing?
Yes, exactly, like Pegasizing.
Oh, what there
Or
is,
Johnnicizing.
Johnnicizing, yeah, it is.
Okay.
Yeah, they read their Quine.
But you have unique identifiers like corresponding to the singleton sets of each member.
Yeah.
Okay.
You think about it like this, like the identifier is just picking out John. Under the hood is interpreting Like it's spelled out in the machine, like at a little bit lower level in a different way. Like, and this is, again, the theoretical underpinnings for what you see on your screen, right? And like the syntax when you're like building stuff out in Protege is like a simplified view. It doesn't show you exactly what's happening at a logical level. In fact, you'll see this in several points because this is not the only surprise. Protege does a lot of things that it doesn't show you the details about. Well, we'll see the details. That's part of the reason we're walking through this. You can only be used combined classes. That's why we get that. Okay. Now to the interpretation. Remember, that was just syntax. That was just the symbols and combinations of them. What does it mean? I'm not going to make you walk all through this. I've got a picture that illustrates what's going on, but I do want to just highlight some things. Just one. Interpretation is what we use in logic often. It's like a standard locution that we use to map the symbols to the world or the symbols to a domain. We say that's an interpretation function. This interpretation consists of a non-empty set called the interpretation domain. This is a set and a mapping that maps every concept name to some subset of the domain, every role name to a binary relation in the domain. That's basically it. That's it. And I'll show you a picture of what that looks like in a second, but I want to show you this. If you were reading this equivalency, like this, what this is saying is like the mapping here of the C intersection with D is the same as the mapping of the C's into the domain intersected with the mapping of the D's in the domain. So the interpretation kind of moves out, moves in. And you'd read it just like this, left-hand side, from the left to the right. The interpretation I maps the conjunction of C and D to a set, S. Right-hand side, right to left. The intersection S prime of the set which I map C to and the set which I maps D to, that's what this side of the equation is. And what this equivalency is saying is that the statement asserts that S is equal to S prime. That's it.
What if you mess with those distribution rules for the interpretation?
Well, then you get some perhaps interesting logics that may be discussed in Graham Priest's Introduction to Non-Classical Logics.
Right. So I was thinking it would be like you get rid of some sort of like reduction.
You might like Restall in relevance logic, and his work on relevance logic plays around with some of the upper level constraints like this. And they have like ramifications of things like conjunction doesn't work the way you think. You can't like reproduce the same element or line in a proof more than once because it's verboten. And also like negation works differently. But yeah, Restall, Greg Restall, R-E-S-T-A-L-L, relevance logic.
Are you connecting the square ones and the round ones intentionally like these, or they are the same?
So this on this side is technically like a set operation. Or one of these, let's see. Oh, one of these is a conjunction and the other is a set operation. And they are different symbols because they're doing different things. Like one's inside the scope of, one's inside the scope of an interpretation. So one's a symbol and the other is supposed to be in the domain. As you can see here, this is the picture I was talking about. This is what interpretations do. You go from the vocabulary down into the world or the domain, like an individual name. You see that right here in the domain. Class names are also in the domain. You see this little, the delta with the I, this is the domain. And then role names or relationships, those are mappings from the relations to pairs of things. This is going to be very important for the project. This specific side, the role name mapping into pairs is going to be very important for the. We're going to be thinking a lot about pairs of things and how they relate to other pairs of things. Just FYI. And to my mind, as a logician looking at OWL and the way it's used, I know there's like a tendency for folks in our circles not to use relations very much. They want to minimize the number of relations. They think they're overly complicated. That's insane to me. That's where all the logic is. Relations are how you take one part of the hierarchy and connect it to another. Classes do very little. So we're, again, just to give that carrot again, we're going to explore the space of logical connections through relations because that's, again, where all the logic is And it's silly that we haven't been doing it. I can tell you why later, why we haven't been doing it. It's mostly because people don't know how they work, but that's what we're gonna do. We're gonna address how they work and give people a cheat sheet so they can use them like I do. By simulation theorem. Did you guys think that was heavy so far? You guys okay? Feeling all right? This is about to get heavy. Up until now, we've seen examples of differences in expressivity. ALC, for instance, doesn't have a constructor for inverse roles. So I added this thing. And I mentioned, I was like, I'm just saying you can't express this in ALC. I'm just saying you can't talk about inverses. I'll show you a proof later. Examples are just suggestive. It isn't yet clear, for example, that a constructor for inverse roles can't be defined using only ALC syntax. If such a constructor can be defined, then ALCI, that inverse language, is not more expressive than ALC. If you can say inverses and represent inverses in the same way, just using ALC, then they are at least as expressive as one another. I will prove to you that the inverse version is more expressive than ALC. I'll use a bisimulation strategy for demonstrating this. It's from John von Bentham's dissertation back in the 80s. He created this. It's actually applied to modal logics to show how one of like different flavors of modal logic are more expressive than others. But it is challenging, as you know, to prove a negative. And what I've said is you cannot define an inverse role constructor in ALC as a negative. How would I prove that? Bisimulation is the way I proved a negative via an indirect route by generating a contradiction. This is bisimulation, the theorems itself, the characterization. I will not make you read this. I will just let you look at SpongeBob. Logic. But what I will do is I will walk through examples because I think this is an easier way to understand what's going on. So, bisimilar, the relationship that you can prove between structures in a graph. In this case, I'm going to claim that D1 here is bisimilar to F1 here. Intuitively, what this means is that the structure that D1 points to is mirrored in F1. Now, hopefully you can see that. You can see that D1 points to D2, which points to D3 and D4. D1's M, D2's M, M, F. And you can see that here, F1 to F2 to F4, F4 or 2 to F5, M, 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 F, same over here. The structures are mirrored. Okay. The first step in proving bisimilarity is the invariant step. First, you check to see whether the things you're testing for bisimilarity are of the same type. And in this case, and you can think of it very much like these are instances of a class, and they're both instances of M, and that is true. First thing you do. Second thing you do. If there's a role, in this case C, that relates D1 to D2, as this does, then zig over, there has to be a mapping from D2 to F2, right there, such that where D2 and F2 are both instances of M, and they are, in mapping that structure, and role C maps F1 to F2. Right? Just tracking, I'm just tracing down the structure. It's the zig direction, there's a zag direction, and also, of course, F1 to F3. Now, the zag direction, there are the three steps, the invariance, zig, and zag, okay? So zag, if a role C relates D2 to D3 and D4, like it does in this case, there has to be a mapping over to F4 from D3 to F4 and D4 to F5 as well, from D3 to F6 and D4 to F7, where D3, F4, and F6 are instances of M, and D4, F5, and F7 are instances of F, because that's what you see on the left-hand side. In addition, C relates F2 to F4 and F5, and related F3 to F6 and F7. Basically, what I've done is walk through that intuition where I said you can mirror the structures on both sides. This is a decision procedure. This is a stepwise procedure you can implement. You can code this, and people do. You can, in fact, as we'll see, as we'll do, write a Sparkle query to check this. I'll show you how. Now, That's an example where these two structures were bisimilar. These two instances, these two nodes are bisimilar. They have the same structure coming out of them. Let me give you an example when that does not happen. I'll claim that D1 is not bisimilar to E1. So, and intuitively, you should be able to see this. The structure here, D1 is pointing to D2, which is pointing to D3 and D4. E1 is pointing to E2, but it is not pointing to two things. E2 is not pointing to two things. There's a break in the structure. They're not mirrored. They're mirrored up to one point. Now, they are both instances of M, so invariance is, that's true. Now there is a role C relating D1 to D2, and if that is the case, there should be a mapping over to E2, from D2 to E2, where D2 and E2 are both instances of M, which they are, and from D2 to E3, where D2 and E3 are both instances of M, which they are. Got to map the structure, both sides, right? And role C maps E1 to E2 and E1 to E3, right? So far, so good. That's what I said. They're bisimilar up to a point, up to this point. Now, for zag, the other direction, the third piece, if role C relates D2 and to D3 and D4, as it does on the left-hand side, there has to be a mapping from D3 to E4 and from D3 to E5, such that D3 and E4 are instances of M and E5 is an instance of F. And C relates E2 to E4, and C relates E2 to E5. But C does not relate E2 to E5, so they're not bisimilar. That is where it breaks. Again, this is just a stepwise procedure that should be capturing the intuition you had. Are the structures mirrored? No. How do you show that? Well, this is a simple example, right? Yeah, John.
Could you also, does it satisfy to say E2 does not correlate to E5, but you also say E3 does not correlate to E4?
Yeah, absolutely. It works the other way too. It's like the structures are similar. In fact, if you did have a link between E2 and E5, this would still not be bisimilar, because there wouldn't be E3 to E4.
Yeah. It would only be bisimilar if E2 and E3 were going to both E4 and E5.
That's right.
Yeah.
Yeah. What's that?
So, I mean, like, this looks to me like it's just telling if some set of sentences holds true under multiple different interpretations, right?
Oh my, what a
Like,
lovely thing to think.
I mean,
You can characterize
is that
like
literally just a different way of talking about
It
what's
is,
happening here,
it
or
is.
is this something that applies
definitely is.
specifically to?
if you were taking like logic in a CSE department,
Yeah,
or you're taking like discrete math and like working through some of the advanced courses, you would see descriptions of like what we would call propositions
Mhm.
that are true or false of different models. You'd see them often characterized as graphs, and
Yeah.
being able to distinguish or not distinguish graphs. There's a translation between them.
that-
In fact, like a lot of like, if you were like to open a computability and complexity theory book, they all use these graphs, right? Like these kind of neuron graphs, so called.
Yes.
But there are propositional translations about them. In fact, I'll show you.
Jordan.
So look, the language of ALC, as I've claimed, is not expressive enough to distinguish between bisimilar elements of a certain sort. So bisimulation is a relationship between the interpretations and elements, and interpretations are distinct from syntaxes. So we can say certain things, and sometimes we capture the same interpretations, and sometimes we don't. Sometimes our language is expressive enough to capture interpretations, and sometimes it's not. You know, just as a detour here, in the history of logic, Aristotle, you guys heard of Aristotle? It's probably the best evidence that aliens visited Earth, because there's no way one person did all that. There's just no way. Like, he's clearly alien. But Aristotle invented logic, we say, and he invented logic as a syllogistic logic. Started with like quantified sentences, right? All, some not, not all, right? The four categories, and you can build like a lot of logical expressions and syllogisms out of that. Now, it's not everything can be expressed in it. And for like 2,000 years, logicians beat themselves in the head and each other in the head about like how to represent various like boundary cases. And it was to the point where like Kant, when he was writing his logic textbook, was like, the preface says, no progress has been made since the time of Aristotle in logic, because up until that point, almost 2,000 years, people were still just using syllogistic logic and trying to like figure out how to represent various sentences. Here's a sentence they had trouble representing. John is happy and John is bald, which we just use a conjunction, two propositions, but they're like quantified expressions didn't allow for kind of ground level expression representation like that. So they had to do all this weird nonsense, like weird manipulations just to represent that. And in some cases, they couldn't even represent that simple expression or a simple expression like that because they started with like a language that captured only a part of like the bigger picture of how we use natural language. It just talked about all things, some not, and not all. That's it. And they tried to build everything from there. It's not a very expressive language. They couldn't characterize John is happy and John is bald like that. Not with it, they didn't have a conjunction. Syntax is different from interpretation. The syntax can really limit how you can represent what you can represent and what things can be made true according to it. That's the similar situation going on here. Description logics of varying flavors are more or less expressive. Some of them can say things that others can't. First order logic can say it all. It's too expressive. So, for example, bisimulations between interpretations are distinct from the syntax of ALC itself. What does that mean? Check this out. I know you guys are just dying to see an expression written in description logic. So look, gaze at my mighty works or whatever. Okay. For all x, there's some y, such that, actually, I'm not even going to try to read that grotesque language at the top. This is a translation of it in first order logic that's much more expressive. So the top one's description, second one's first order. This says, there's some y, there's an implicit universal there. For all x, there's some y such that c relates x to y, and y is an m. And there's some z such that c relates y to z, and m is a z. And there's some u such that c relates y to u, and u is an f. That is what that sentence on top says in description logic. Now, you just want the English. Any x that has at least one son, who has at least one son z, or has at least one son y, who has at least one son z, and at least one daughter u. Natural language version. Now, here's the thing. Both graphs satisfy the ALC expression. ALC written here, just used ALC like notation. Both of these graphs will satisfy that. ALC syntax can't distinguish these graphs. ALC can't distinguish bisimilar graphs. It's not expressive enough to say that's one interpretation, that's a separate interpretation. As far as ALC is concerned, they're the same interpretation. Here's how you show this. Yeah, we'll see. I'm going to show you by pointing to something that ALC can't express, but ALCI can, a distinction. So let's say there's an ALC inverse concept class, that is class, such that that class is not equal to some D class that holds for all ALC concepts D. Put another way, recall that ALCI adds just that existential nonsense, that existential quantifier to the syntax. To prove that ALCI is more expressive than ALC, we just have to show there's no expression in ALC that is equivalent to the inverse. Suppose there is such an expression in ALC, call it D. We'll show that this leads to a contradiction. And here's how we'll do it with bisimulation. Consider D2 and E2 in the following diagram. They're at the bottom. There is a bisimulation between them, which just means that E2 or D2 is in the domain and E2 is in another domain. So they exist. However, D2 has an inverse, has something that's relating, that could be related to it. And it can say that, it can express that. E2 does not. putting this another way. If you're thinking about bisimulations, you're thinking about the structure that emerges like downwards in the graphs, right? You're thinking about what comes out down. What's the structure that's mirrored downwards? There's no direct way without an additional resource from a language that you're describing to look backwards. You have to add that in. In this case, all the bisimulation resources from ALC provide are just a way to look forward, not backwards. That's why E2 can't say something's looking at me. D2 in ALCI can, because it has an inverse. Which is just to say, if you have a language like ALCI that has inverses, you can distinguish these two cases. Because in that language, because you have inverses, D2, you can say from D2's perspective, something's looking at me. It's the inverse R. You can't, and there's nothing in E2 that you can say. You don't have to. I mean, you've distinguished them. There's nothing looking at E2 and you can show that. There's no inverse. If you're just looking at this from the perspective, if you just have the ALC language without inverses, you can't say the first thing. You can't say something's looking at me. And so as far as ALC is concerned, these things are the same. Does that make sense?
I understand the inverse and the X and why it can't. I don't really understand how there's a bisimulation in the first place between D2E to DI1 and E2E to DI2.
Mm-hmm.
Is that because, oh, okay. So we're just saying that D2 and E2 are the same, can be the same in this language, but then they're not because it, okay. I think
That's it. Yeah, you got it.
Okay. I thought it was looking at the whole structure on the left and the whole structure on the right,
Yes,
okay.
like that, and whether you can or not depends on the expressivity of the language. That's kind of the point here, right? Like,
Yeah, no, that makes sense now.
good,
Yeah.
good. Yeah, in some languages, you have the additional resources to be able to look back in this case, and in some you don't. ALC, you can't look back. ALCI, you can.
So I'm guessing OWL uses ALCI because you have.
Actually, so we'll see next time when we go. I'll go through the acronyms, but OWL uses SQORIR, which is like S is ALC, and then there are there are cardinalities, there are nominals, inverses, and I'm forgetting what the R is. Regular roles. That's right. Role constraints. That's right. Role constraints like functionality, symmetry, etc. Yeah.
So with your previous example with the more nodes, you would be able to use ALCI to like backtrack from the nodes. I think they were on like the right corner back in order to see, okay, that doesn't match up to the other one.
Yeah, you can this is a good way of thinking about it. You can backtrack up and say, look, what's pointing at me?
Yeah.
Now that's the crucial piece, like just for your intuitions. ALC doesn't have the ability to say, if R is looking at D2, it doesn't have the ability to say, there's something looking at me, because it doesn't have the resources to relate itself to whatever's looking at me. That's what inverses do. And so because it doesn't have that expressivity, ALC treats these as the same. Here's another example. Well, actually, let's spell this out. ALCI expression can be satisfied by D2, but not a E2 on the right, since the latter lacks any role to have an inverse. And because there's a bisimulation between them, and existential, and D2 satisfies the existential, but the inverse existential, but E2 doesn't, ALC can distinguish bisimilar graphs that ALC can't. Now, another example, expressivity again. This time we'll focus on ALCN and show it is more expressive than ALC. Again, this is one with cardinality constraints. Same setup. It'll always be the same setup. To prove ALC, that should say N is more expressive than ALC, we must show there's no expression in ALC that is equivalent to less than or equal to rho 1. It's just a simple case. Suppose there is such an expression, call it D, we'll show that this leads to a problem. Here's the graph. There's a bisimulation between E1, just in case there was, E1 is in the domain as well. And while E1 is related to less than or equal to 1 things, E2 is related to more than that. ALCN, if you add this constraint in your language, this cardinality constraint, you can distinguish these two. ALC, if you recall, does not have any such constraints. It can't distinguish them. It can't tell you you can only look at this many. And so as far as ALC is concerned, E1, E2, by similar, they can't distinguish the graphs. But again, so important, just kind of, if you've taken away an intuition here, distinguishing graphs leads right into expressivity. The more graphs you can distinguish, the more expressive you are. The more distinctions you can draw, the more expressive your language is. First order logic can represent John is happy and John is bald. It's more expressive than syllogistic logic, which can't.
I mean, this is, I'm not sure if this is like even like a well-formed question, but using the cardinality rule, like that looks like it requires that you be able to range over relations or these rules. Like you're ranging over nodes, right? You're saying there's
No nodes, not the edges.
edges, excuse me, that's what I meant, is that you're ranging over edges, but that's gonna come down to sets, so you're ranging over sets of sets, so you're no longer in first
Instances
order.
of sets.
Okay,
And John, this gets back to your original point that you want to prove it in the real world because and you were talking earlier about people not using OWL, or it might be because they didn't have to. Like if
Yep.
I work for a telecom company and I create a RDF graph, I might only care about 3 different nodes, like three different universals. So therefore, my system doesn't have to be as expressive as say other systems that are going to have similar graph structures that are utilizing different universals or different instance data. Correct? I mean, that's why we would need this, right?
Oh, yeah, yeah.